I will replace Muli today. He caught the flu. And I'm going to present to you the latest changes in NVMe over TCP. So for anyone that is not familiar with NVMe TCP, it was just recently ratified, but we'll talk about it later. It all started in 2014 when we got the initial NVMe over RDMA pre-standard. After that, later in the same year, we got the NVMe over Fabrics standardization, basically the 1.0 standard. In 2015, NVMe.org basically formed a group, a task force of key developers that together converged all the code, the existing one that was already in 2015, together with the over the Fabrics transport layer, into one main Git repository when all NVMe developers could work on the same baseline. It was pretty much heavy lifting of the already existing code together with implementing the new Fabrics code, basically the RDMA that was exist in the same time. And in 2016, all the baseline basically was merged into the kernel. It was kernel version 4.8. So what we had since then? First of all, hardening. Various stability fixes. NVMe over Fabrics was pretty new in the Linux kernel and in the ecosystem itself. So we needed to create a better ecosystem and to adapt the code and the drivers to be broadly deployed. So many fixes in the transport layer, in the Aeroflow, in the control plane, everywhere. Second thing was tracing support, because if you will give someone a driver and you will not give him the ability to debug the driver, it basically makes everything much more harder. Additional transport was introduced. Basically, it was the fiber channel transport, additional to RDMA that was already deployed and was already in the upstream kernel. We had a few toolchain enhancements. Those are basically attributes for those of you who are more familiar with the NVMe session. So those are attributes of the controller. So we had queue size, NRI queues, and all kinds of other attributes that can be used if you're familiar with the over the Fabrics protocol. Compliance. So UUID support was added. UUID support is mainly important if you want to stay consistent with the namespace and give a uniqueness to each namespace that you're using on the target side. Also, we had a few other enhancements. One of them is the Opal support, which is available only in the PCIe driver. IO polling support, which is currently available only for the RDMA driver. And ANA, which is the asymmetric namespace access, which is basically, it's pretty interesting because it's kind of, you can optimize the way you're addressing a namespace over the fabric. So it was also introduced in 2016. But we are here to talk about the NVMe over Fabrics 1.1 standard. What was introduced in the NVMe over Fabrics 1.1 standard? First of all, and in my opinion, the most important one, it was the NVMe over TCP. So NVMe over Fabrics in general got mainly adopted using RDMA. Few of the users also used fiber channel, but part of the puzzle was missing, in my opinion, which was the NVMe over TCP. And we'll talk about it in a second. 3 different things that was introduced during the 1.1 version are dynamic resource enumeration. Basically, dynamic resource enumeration gives you the opportunity to stay connected to the cluster that you're working with. So in case a new subsystem is introduced in the cluster, you're getting notified about it, and you can basically learn about new subsystem and decide if you want to increase your cluster or same with the same size of cluster. Second thing is the SQ flow control disable mode. So again, for those of you who are more interested in the specific NVMe PCI, you know that in the completion queue entry, the NVMe controller should return the SQ head. So in Fabric, it hasn't been implemented because it doesn't have any valid use case that anyone found, as far as I know. So in the 1.1, basically, they gave the option to disable it, so you will not need to return it to the host. And the third one is the traffic-based keep alive. So we learned that sometimes NVMe Fabrics has a mechanism of keep alive that should tell you that the connection is still alive and you don't need to go into error flow or reconnect it. So in 1.1, we introduced also a traffic-based keep alive, which means that if you have traffic on this connection, you don't need to wait or to submit a keep alive because you know the connection is alive. So any IO you get, you basically trigger no keep alive is needed. So it helps in case of high congestion networks, which is very important, especially in TCP. The Fabrics Linux driver task force is developing the technical proposal to both drive the spec and provide early adoption. So most of the features that was introduced, including NVMe or TCP, it was very important for us to first adopt the features so we could build the ecosystem and bring much more mature product or standard before ratifying the actual standard. So why NVMe or TCP? First of all, it runs on anything. You don't need any special hardware. You don't need any special infrastructure. You just need a plain Ethernet network that you can run TCP on it. TCP is probably the most common transport. I think that all the people in the room had the chance to experience some TCP developing or using or something like that. High performance. TCP delivers excellent performance scalability. We'll talk about it later to see how NVMe or TCP especially uses the TCP scalability, but also TCP as a protocol has its own RFCs and features to increase scalability and performance. Well suited for large-scale deployments and longer distances. So TCP, because it's based on Ethernet, it is routable. It is easily deployed on any infrastructure, like said before, and it's pretty easy again. And actively developed. So TCP is a protocol that is well maintained in the kernel. There are many key developers in the kernel, in Linux upstream, that are developing the TCP protocol every day and maintaining it and solving bugs. And it's really important that you want to deploy a new protocol that you have key developers that support it and you don't need to maintain all the ecosystem by yourself. So NVMe TCP ratification, actually, it's pretty new, okay? It's like 3 months ago, NVMe TCP was ratified, November 15th, 2018. Multi-vendor joint effort to ensure interoperability. Okay, there are multiple vendors that are trying to push NVMe TCP ecosystem to be broadly deployed. Designed for simplicity and efficiency, as we already mentioned. And we also had a first NVMe TCP PlugFest POC, which showed how many vendors are trying to deploy NVMe TCP and to develop their own products based on this new transport binding protocol. So after describing in general the protocol itself and the history of it, let's talk a little bit about the association model, because one of the important points in NVMe Fabrics in particular is the abstract of the transport above the regular standards of NVMe. So in NVMe TCP, each controller association maps one-to-one NVMe queue to a TCP connection, and it has its advantages. First one is no controller wide sequencing. If you had the chance to work with protocols that has multiple queues per session, you know that sometimes if the sequence should maintain between different queues, it can cause a lot of problems of fairness and ordering. Second problem that basically was solved during this using this mapping is no controller wide reassembly constraints. If you lose a packet on one queue, it doesn't mean that the other queues have stopped working on something. You can keep on working with all the queues because each TCP connection is mapped to a single NVMe queue. So the connection binding is actually performed during the connect phase. When you're creating the controller over the fabric, you're mapping all the queues to different CPUs. So this is actually, we're going to talk a little bit, we're going to dive a little bit deeper in the protocol itself. This is the enhancement of NVMe or TCP above NVMe or fabrics, the protocol data unit. Basically, every NVMe or TCP message is encapsulated in such a protocol data unit or PDU. Every capsule and data, okay? It means basically every message. PDU structure varies per PDU type. So as you can see, the 8 bytes on the top are common header because you have multiple types of PDUs. And below it, you can find the variable length PDU. PDU optionally contain header or data digest. Okay, this is we'll see it, but we're using the data digest from the Linux kernel. So again, we don't need to implement anything new or maintain it. We're using the generic APIs from the kernel, which help us to push it further. Also, it has padding in case it should be used for alignment enhancement for all kinds of specific hardware that needs the alignment in the PDU. So if we will take a look on the right side, you will see on the top the PDU header. This is a common header. After that, optionally, you can use header digest. After that, you can see the padding between the header of the data if needed, then the data, and then the data digest itself. So what are the PDU types that we have? First type is the initial connection request and response. Those are not exist in NVMe or fabrics, the non-TCP type. And basically, it's kind of negotiation between the host and the controller about the connection that they are going to build for the NVMe or TCP. Second PDU type is, okay, we'll see here a lot of H to C, C to H. So H is host, C is controller. So basically, in terms of storage, host is the client side, controller is the target side, or server and client. So host to client termination request and client to host, controller to host termination request, those are basically PDUs that are meant to be used only on error flow. Okay, you should not see those PDUs in regular flow. They are used in case the NVMe over TCP stream got out of sync and one side want to tell the other one, okay, I'm going to close the session. If you want to do something until then, I give you your time. You can do analyzing what happened. You can dump traces. You can see the latest messages on this session. And then it closed the connection. If for some reason, if you lost connectivity or something bad happened in the network and you send a termination request and you don't get any completion, so eventually you are just closing the TCP connection and you rebuild all the connection again. So third type is the capsule command and capsule response. Capsule command and capsule response, for those of you who are familiar with NVMe over fabrics, basically encapsulate all the NVMe over fabrics command. So each write command, read command, discard command, connect, for example, are all encapsulated in this kind of capsule command, and the completion part is encapsulated in the capsule response. Next type, host to controller data and controller to host data. Basically, in NVMe or TCP, there are two ways to send data, basically do writes. The first one is using inline data. Inline data is a size that the controller is exposing during the connection phase. So you can send data together with the PDU, basically with the command itself. The other way is to use non-inline data, of course, which will be talked about later. And here in this part, host to controller data and controller to host data means that it's only data. It doesn't have any command, and it's really important for the controller because the controller basically has its own state machine to know if he's expecting a data PDU or a command PDU. Last type, but very important one, is the R2T, ready to transfer PDU. So for example, let's imagine a scenario when the host wants to do writes to the controller, but the controller doesn't have any free memory for it. When you're working with TCP, comparing to RDMA, for example, you need to read all the data into some buffer. You need to have some buffer to read the data. And the host can't know exactly what is the state of the controller and if he has the free space to read all the data. So that's exactly what we're using R2T for. For example, if the host is sending write command and the controller is not sending back an R2T, the host is not allowed to send any data. Okay? It has to wait until getting the R2T. Inside the R2T, it can find the size that the controller assures it has room for. Okay? So basically, there can be, from the standard perspective, few R2Ts in parallel, but currently Linux driver supports up to 1. So we'll see the diagram in the next slide, but the flow is write command, R2T, data, 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 and maybe then another R2T, data, data, data. Here you can see the flow of read command and write command. So as mentioned before, you can't see here if it includes inline data or not in the write command, but let's say this is non-inline data. So on the right side, you can see the host side is sending a write capsule command to the controller. Then the controller returns R2T with specific amount of bytes that we can't see here, and only then the host can start sending data. When the host finishes the amount of bytes that he received in the R2T, he will wait until he will get a new R2T, as can be seen here. He gets another R2T, and then he proceeds sending data. After all the data has been sent, the controller is sending the completion for the I/O. On the left side, you can see a read operation, which is much more simpler without the R2T, because if the host is initiating a read command, we are assuming the host has enough buffers to get all the data. We are not expecting the host to send the read command without free buffers to get the data. So the minute the host sends the read command, the controller can start sending data, and then the completion when it finished the data. So what about the Linux support? Like any other standard, if you're not in Linux, you're partially not exist. So the same task force, almost, that was used for the NVMe over Fabric standardization and development was used here. They converged the NVMe over Fabric's code into a different repository to develop and maintain the NVMe over TCP until it was ratified. It was the same procedure like with NVMe over RDMA, where the code was developed on a side repository, but was started to get used to, and people started to contribute and to change the spec and the standard depending on the feedback about the code. As the spec evolved, as mentioned, code adjustment followed providing feedback to the standardization. And finally, we can all find this code under kernel 5.0 or 4.21, to those of you who are not familiar with it. It's currently under RC5, but code is pretty solid. Okay, it's well deployed in the latest POC that we had during the PlugFest. There were multiple vendors that were using this code, run, check interoperability, and everything worked. So you can use it, and I suggest it. So what were the driver design guidelines? When we designed the driver, we actually needed to add another transport binding to the already exist RDMA and fiber channel binding. So we implemented single reactor thread per CPU, and we had our reasons. First of all, we wanted to decrease the amount of context switches as possible. So we have only single thread that is running the reactor and waiting for Rx and Tx. And also, NVMe queues are spread among reactor threads. So you're still living in a world with multiple queues that are running on multiple CPUs, but each CPU is handling its own queues. There are no shared queues between CPUs. We never block on I/O, unlike other TCP implementation. So we can use the CPU for any other thing, but we can also do things very fast. Sorry. We aggressively avoid data copy. So today in kernel 4.18, I think, we were introduced with RX zero copy, but it's still not available in current upstream driver. But we do use TX zero copy, so we basically don't copy any data on TX. We also minimize the number of allocations on data path and the atomic operations that we use. We try to avoid them. Basically, I don't think there are any today, atomic operations in the data path in the driver, only in the lower layers. We reuse common interfaces. So when developing a kernel driver, basically a one that you want to be mainly deployed and mainly used, we used all the generic APIs from the block layer and IOV header, for example, and socket and datagram operations. So we will not need to change anything when something is changed in the kernel because it's well maintained. And if someone is changing a generic API in the kernel, it will change it also in all the drivers that are using it. We didn't want to write our own iterators, which are hard to work with and you need to maintain and you need to be very careful not to break. RX is handled on the same reactor context. So for those of you who were familiar with the original NVMe TCP code, when we started to write the code, the RX was handled during a soft IRQ context, and sometimes during and sometimes in the reactor context. We changed it. In the updated code, all the RX processing is being made in the reactor context. So we don't block the CPU in soft IRQ context. We finish the soft IRQ context as fast as possible, and we basically return to the reactor thread. So as mentioned before, we also try to keep atomic operations to an absolute minimum, and we implemented fairness and budgeting mechanism multiplexing between NVMe queues. So this is interesting because think about a situation when single CPU is handling more than one queue because it got connected to different controllers because I don't know why. So we have mechanisms that are assuring that each and every queue will get his bandwidth, so you will not have starvation on single queue because the other queue is always got something to process. Here we can see the NVMe host stack with the addition of NVMe TCP. Nothing was changed from the existing stack. Maybe some small changes in the control plane, in the error recovery, but nothing specific for TCP. Control plane is very similar to RDMA. Okay, we use the common code. We moved a lot of code. We will see it in a bit. We moved a lot of code to the common core driver in the NVMe drivers. And we still have plenty of room to improve it, which we plan to do. On the target side, it's basically the same issue. Didn't change anything. We just added one file called tcp.c where we implemented all the TCP transport, but we integrated it with all the other transport bindings that were already there in the NVMe Fabrics driver. So again, very few changes to the existing core Fabric stack. And here is what I talked about. Those are the code distribution between different drivers in the NVMe Fabrics drivers today in Linux. So I hope you can see it, but TCP and RDMA has the same percentage of code in the NVMe Fabrics driver. Most of the code is moving to the shared driver, which is the core driver. So the Linux subsystem is in pretty good shape, most of the code in common. And again, still, we have many room for improvement, and we are also working on it. So next issue I'm going to talk about are two problems that we encounter. In my opinion, those are very interesting problems that we encounter while developing NVMe TCP. First one relates to data digest. Because we use the SKB datagram interface in the NVMe TCP host driver, we basically got data in fragments without knowing actually in which chunks actually the NIC provided the data. We got SKB and we can and need process the data. But we want to do data digest. We want to do CRC or something on the data. So we have two options. First option is to wait for the whole message to be received and then go over all the message again on the data and to create the data digest part. But because we want to touch the data and to process the data while the data is still hot in the cache, so we develop a new interface that's called SKB copy and hash datagram iter, which help us to do the data digest while processing each and every one of the SKBs. So basically, we don't need to copy all the data and then perform the digest. We can do it on the fly. So we have a new struct also that's called a hash request that we pre-initialize for every new message, which help us to maintain all the data digest on the fly part. And we also don't have our own iterator over there, so we don't need to maintain it. We just contributed it to the Linux upstream, so it's basically there. Second problem we encountered is when you're working with NVMe TCP, the headers of TCP, the headers of the PDU are pre-allocated. We don't want to allocate header per message because it costs us in performance. So they were pre-allocated from the memory allocator, aka the slab. Like any other buffer, PDU headers are never copied, so we use kernel sendpage to send them. Basically, we don't copy them anywhere in the data path. And we saw some rare cases under high congestion that PDU headers might get coalesced together. What does it mean? It means that you're doing send page and you have more than one header in that page. What is the problem here? The problem that if you're working with kernel hardening, you will get a panic when user copy attempts to read slab originated buffer if they cross slab object. And I will explain how user copy relates here. There are user space programs that allow the user to copy a complete packets into user space. So in our case, we found out about it using DH client. DH client decided randomly to copy packets from the data path of NVMe or TCP back to user space. But sometimes when the network was very congested, it caused us for kernel panic. So this is, first of all, security problem. This is also a driver bug because you don't want any of the deployers of NVMe or TCP to get kernel panic because of DH client or because of BPF or tap device. How we solved it? We solved it basically, we improved two things. First of all, we solved the issue, you will not get panic. Second, we improved performance a little bit. So we introduced something that's called page frag cache. We didn't introduce it, we used it. This is a kernel struct. And we implemented to be an attribute per queue. So page frag cache is actually a mechanism to allocate memory, not using the slab allocator. It's using the actual pages of the kernel, but it has the logic to allocate only small object out of the page. So also we didn't have any cross-page reference. So each core handled its own pages, and we didn't have to do any cross-cores ref counts on those pages. This is already upstream. Features. So as we talked about, zero copy transmission already there, supported, worked great in my opinion. Header data digest also supported. Header data digest also supported in the user space tool called NVMe CLI. You can decide if you want to use it, you don't want to use it, really important. TLS support, encryption, in the future it will be implemented. There are a few experimental branches to do. Polling mode IO, currently not available, but in the plan. Automatic receive flow steering. This is a real important feature that currently we are investigating to understand the NIC steering table updates and the effect it has on the performance. And out-of-order data transfers. So out-of-order data transfer can be used for multiple use cases, but the most interesting one, imagine a use case when you want to read 1 megabyte from the controller side. And the controller side somehow can bring you the latest 128K before it can bring you the first part of the data. In current situation, it will not send any data not in order. So basically, you can get yourself into a situation where your network is much more congested, where you can free it by sending by sending part of the data before. In-transit encryption TLS. So currently, TLS encryption negotiation is not supported in the kernel. It is only supported in user space. So we have two options to implement TLS negotiation. We already decided. It was proposed that TLS encryption will be an attribute of the port, because we don't want the client side, the host side, to decide if you want to use encryption or not, because it sounds funny. Because if the controller wants to use encryption and you want your data to be encrypted, you can't give the host the opportunity to not use encryption. So first of all, this is an attribute of the port called TSAS, and it can be discovered during the discovery mechanism in NVMe or Fabrics. And we have two options to implement it. So the first one is to trample into user space the negotiation of TLS. Second one is to port TLS handshake into the kernel. Support is expected pretty soon, I guess. It's already work in progress. So stay tuned. And we can't finish without talking a little bit about the performance of NVMe over TCP. So I'm aware that people are afraid that NVMe over TCP will not give you the required performance, the required throughput, and the required bandwidth. But as we will see here, you get very close to RDMA. Of course, RDMA has its advantages, but it depends on what you're looking for. Because as you can see here, although it looks like the difference between TCP and RDMA is pretty big, but if you will look at the y-axis, you will see the difference is, sorry, it's hard for me to see, but I think it's something like 20 microseconds or so, both read and write. And 20 microseconds is not a high number when you work with, for example, SSD. So latency is pretty good. Also in the tail latency, it's very hard to see any difference. By the way, this is a QD1, so this is very, very important benchmark. About scaling with threads, also something that people want to achieve. They want to be scalable. They want to add CPUs and get higher throughput. As you can see here, also, you get it in TCP. So you're getting your CPU work a little bit harder, but as long as you will add CPUs, you will get higher throughput. About the latency that I hope you can see, this is the yellow line, the increase that you see on the 16 thread is only because this is a system of 12 CPUs. So actually we had more threads than CPUs. So you get the latency penalty because of that. If we would test it on a system with 16 threads, 16 CPUs, you will not see any difference. And last but not least, the CPU utilization. So because we are doing a one copy on the RX, on the host side, reads are much more expensive than the writes because we copy the data. But as you can see also here, when we are increasing the block size, this is the performance that you want to see, because we have all kinds of features related to TCP, like LRO, which is large receive offload, or TSO, which is TCP segmentation offload, which are very helpful when you're working with large block size and give you the opportunity to move part of the compute into the NIC, for example, in this example. Also, target CPU utilization is roughly half than the host because of the reads, but not only.